Okay. So one of the classic ways of determining whether things are able to conduct electricity is to set up an experiment like this, where you have a light bulb, and as you can see, if the electrodes are touching each other, like metal touching metal, the electricity is able to flow through, and you guys will get a light. It will glow. If the electrodes are not touching each other, electricity won't flow through. So if there's an electrical solution or a solution that's able to conduct electricity, then it'll act as similar to these electrodes touching each other. So then the electrons are able to flow through to complete the circuit. It's kind of like, you know, like when you guys turn on your switch, your light switch in your room. Hello? Anybody there?
Mm-hmm.
Yes.
Yeah, sorry, I was on mute.
Okay. So when you guys turn it off, what's happening is that your connection is going to be broken. So it's kind of like this case where they're not connected to each other. And then when it turns on, the connection is in place. So it's kind of like these guys are touching each other. So like I said, if we have a solution, right, that is able to conduct electricity, then we're able to get light to flow through. I mean, able to get electricity to flow through, or electrons flowing through. Oops, I'm getting carried away here. Okay, so if we have a polar solution, let's say something like ethanol, right, or a polar solution, or a non-polar solution, covalent solution, something that doesn't have charges, complete true charges, then we're not going to get any electricity flowing, right? So like water, ethanol, things like that. You put the electrode in water, you're not going to get any electricity flowing through that molecule, right? And so then you're not going to get a light. Now, if I put ions into that solution, a positive and negative ion, then I'm going to get electricity flowing through. If the ion is completely dissociated, meaning that there are just ions there, it's going to give me a strong signal. It's going to be a strong electrolyte. So then that means that we're going to get a really bright light showing. If I have a weak separation, or where I have the majority of the molecules are together and only a few of them are apart, kind of like a weak acid, and that's kind of like the definition of a weak acid, is that the majority of the molecules are together and they're not separating into their ions, right? So in that case, like acetic acid, then in this situation, I'll have a weak signal. So my bulb will look a little dim, okay? You guys get that?
Yeah.
So the more I'm dissociated, the more I'm able to conduct electricity in the case of the ionic particles. And you guys understand how water dissociates. It uses its polarity to kind of keep them separated, but it also utilizes the charges, or the electrons will utilize the charge to sit there and flow through that solution. Okay? So electrolytes are basically just the concept of your positive and your negative charges. So when you guys, have you drank Gatorade?
Yes.
So what is the electrolytes in Gatorade? Because doesn't it add electrolytes to your body?
Yes.
Yes,
Yeah.
supposedly it does.
Supposedly, you guys don't believe it? Have you read the ingredients on a Gatorade bottle? Of course, I didn't bring it. Oops. Ingredients on a Gatorade bottle.
Salt, sugar.
That's right. We have salt and sugar, right? That's essentially the major ingredients on a Gatorade bottle, and flavoring. So in that situation, we know that those electrolytes that are being added are going to be that sodium, right? That sodium ion and the chlorine ions, right? And then you could probably have something like magnesium and calcium in there as well, right? So you have all of these ions that are sitting there that are in that solution. And so those are acting as the electrolytes that your body are going to use, right? Because your body, very much like an electrical system, needs to have charges flowing through it, right? Your nervous system. Questions, concerns, Cash? Okay, well, good. Simple so far, right? So an electrode is basically, it's those two little metal things that are sitting in solution, right? And they're able to sit there and conduct electricity. They allow electrons to enter and leave, you know? And then, and so your electricity, your electrical charges are able to sit there, go in and out of that, out of those electrodes. So electrolysis is basically when your electrons are passing through the electrolytes, sorry. And so again, it's that solution. Electrolysis is the act of actually passing the electrical charges through that. So your electrons are just flowing through there, okay? So, and you guys know that an electrical current is just the movement of electrons, right? Through metal or through solutions. Are you there?
Yes.
Yeah.
Okay.
Yeah.
I know it's Monday, right? It's Monday and you just took a test and you're like, God dang, I have to keep going with Kim. I need you. Need you here. Okay. So I'm going to show you an example again. Okay, so again, here's our example. So we're using the battery as our power source for electrons. So you can see the electrons are going to flow through the light bulb, causing the light bulb to actually light up. Now, if we break this circuit, let's say we just put water in the solution, then the light bulb isn't going to light up. Otherwise, if we have solutions that are charged, what's going to happen is that this negative charge, the electrons are going to flow through here. They're going to interact with these positive charge, and that positive charge is going to cause this negative charge to shuffle, to orient, right? And then so you're going to continuously get your charges, your electrons, flowing through here, because they're just going to be trading charges. So the electrons are going to interact with the positive. This positive is going to interact with the negative, so on and so forth. And then so we get to the point where we flow back through the battery, and then we go through the cycle again. So you're going to have a continuous flow of electrons flowing through there because of your positive and negative charges and how they're going to orient with each other. So a strong electrolyte is basically something that is completely dissolved or nearly completely ionized. They'll say dissociated, separated, right? So it's basically breaking up that cute little couple that were positive and negative. You knew it wasn't going to last. Your mom kept telling you it wasn't going to last anyway. So that's an example of a strong electrolyte. A weak electrolyte is when you have only a little bit of breakup. You don't have a lot of breakup between those molecules, okay? So that's going to give you a weak electrolyte. And I'll show you examples of those too. And we often will talk about weak acids. Because weak acids are just an example of ionic compounds that are doing exactly the same thing. Only thing, that ionic compound is hydrogen instead of sodium, okay? Simple so far?
Yes.
Yeah.
Okay, so non-electrolytes are those that don't separate, right? They don't conduct electricity. They don't have ionic movement, right? So that's like water. Water is connected to itself, although it has a positive and a partial positive and partial negative charge. It's complete, it's together. It can't be separated, where sodium can separate completely from chlorine when it's in water, right? So they're no longer together. You guys see the difference between the two? Water is connected because they're sharing those electrons, where sodium and chlorine, they've given up, like sodium's given up the electrons and chlorine is taking it. So they don't really need each other anymore, right? They're only together by convenience, okay? So once they're in water, then they split up, you know, they dissociate. So this is basically just showing you what I just said, right? In the case of sodium chloride. So we have sodium chloride, the solid, they're going to be together, right? By convenience. As soon as water gets there, water comes in and says, the sodium, hey baby, You look fine tonight. Why are you with this bum? Right? And then as soon as like sodium goes to the bathroom or whatever, water says the same thing to chlorine. Hey, baby, you look hot tonight. Why are you with that chick? Right? And then so it separates the two. Okay? So keeps them separated so they're no longer interacting. So you don't have that plus and negative charge interacting with each other, right? So water is basically that perfect home breaker, right? Or home breaker, what is it called? Home wrecker, okay? So, and that's essentially what it's gonna do with most ionic compounds, right? So if you look at most ionic compounds are dissolvable in water because water is able to separate them from each other, that positive and negative charge. Okay, so this is basically showing you that. So initially when the sodium chloride gets into the solution, water is in the solution. So eventually water comes between them, separates them, right? So you separate your positive and water surrounds it. You separate your negative and water surrounds it. Now this also depends on the quantity of water. If you have only a little bit of water, have you guys ever made warm salty water to gargle? It's been a rough morning.
Yeah.
Yeah.
Okay, so when you make that warm salty water, right, if you put on a whole bunch of salt, are you able to get all that salt to dissolve, or do you have to add more water?
You have to add more water.
Add
You
more.
have to add more water, right? So your water molecules have to equal or be greater than your salt molecule, right? Because otherwise it's not going to be able to separate, keep them separated, because then they'll try to find each other again. Okay. Okay, so this is the same thing that's going to happen in the case of copper 2 chloride when you dissolve it in water. So here's copper 2 chloride as a solid, and then as soon as we put it in water, we put some of it. You can't put it all in there, right? We put some of it in water, it separates, and then our solution gets that nice little blue color because it is separating, and the copper is actually providing the color to it. Questions, concerns, Cash? Okay, so moral of the story is what? What do you guys think you're getting out of this?
Water separates them.
Water separates stuff. Okay, so when it separates stuff, what are you going to get? What is going to be the chemical equation that you're going to get from that water separation? Kind of like what we just saw before. So what is the chemical equation for copper 2 chloride, or chemical formula for copper 2 chloride? Are you there?
Would
Chemical
be
formula for copper 2.
CuCl2.
CuCl2. So initially it's going to be a solid, and if we add water to that, what's going to happen?
It will dissociate.
It's going to dissociate to what?
It's ions.
Okay, so what would be its ions?
Cu2Cl.
2 plus, you're saying? Cu? Is that the ions, or am I forgetting something?
The charges.
Charges. So what would be the charges on Cu?
2 plus.
2 plus.
Plus.
And Cl?
Minus.
Is it balanced?
No.
How many Cl's will I have?
2.
2.
Okay. And we're going to write it as our coefficient because the copper is what's holding those Cl's together, right? It's not the Cl's interacting with each other. Copper is keeping them together. So since copper is keeping them together, as soon as copper is separated, they're able to separate, right? So then that means you have two of those, two individual of those, rather than the diatomic seal, okay? And that's gonna be important. And you wanna put AQ because it's in what?
Solution.
Aqueous. Aqueous stands for what again?
Acid.
Acid.
Well, no, it doesn't only stand for acid. It only stands for acid if there's an H there. Is there an H there? You see a hydrogen there? And this
No.
H
No.
plus, I should say, right? Aqueous stands for what?
Solution.
What was that?
Solution?
Yeah, we've established a solution. What a solution? What? What type of solution?
Solvent.
Did you say Kelvin? A Kelvin solution? Are you guys there?
Yeah.
What does aqueous actually stand for? Look at the word. You want me to spell it
Water?
for you? A U U E O U S. Aqueous. What do you think that stands for?
Water.
Water, right? So anything that's dissolved in water is considered to be aqueous, an aqueous solution. If it's dissolved in ethanol, we wouldn't call it aqueous. We have another solution, but another name for it, right? We would put methanol or ethanol at that, ETOH, to let us know that it's dissolved in ethanol. So you're just letting me know that you've dissolved this in water. So acids are dissolved in water. So that's why they're considered aqueous. The gas is bubbled into water. And so then you're able to form that ion, okay? So it's only an acid if it has that H plus. It's not an acid otherwise, okay? So is this is an acid? Since I have aqueous here, does that make it an acid?
No.
No.
Only if you have the combination of that H plus and that aqueous, okay? That AQ. Do you guys understand that? Yes.
So when you put aqueous, does that mean that it's common knowledge that the H2O is present there?
Yes.
Okay. So
That's
you don't
how
have to write H2O in the
Nope.
equation?
Leave the door
You
open.
wouldn't, well, you're just saying it here. So you want to make it part of the equation because really it isn't part of the equation. It's just a vehicle. It's a medium that you're using to channel things through. It's kind of like, why do you guys drink Kool-Aid? I mean, as a kid, why do you drink Kool-Aid?
Because it's sugary.
Because of sugar. So it's just the water in Kool-Aid is just a medium to help you drink the sugar, right? Because you can care less about the damn water. You want the sugar, right? As a kid. And
Yeah.
as a parent, you want them to drink the water. So you're kind of, oh, we're going to trick them by putting the water in there, right?
Yeah.
Okay. So it's the same concept here. The water is acting as a vehicle for the chemicals, right? So it makes the chemicals easier to react because now you have them already separated. So they're really good. They're ready to react. They're like, okay, let's go. I'm already in my plus stage. You know, I can do what I want to do, right? I'm free. I don't have somebody holding me down, you know? You guys get that? Well,
Yeah,
I
thank
guess we're going to
you.
find out here in a second, right? It's Monday. You can tell it's Monday because you guys are like, is he asking me questions? What does he expect? It's Monday. I ain't
Tired.
answering nothing. I'm too cute. Okay, so let's see. It says write the dissolving equation for K2SO4S. So what do you think that equation is going to be?
Will it end up as an aqueous because it's dissolving in water?
Okay, so then tell me how are we going to write that?
So well, you would use your given, which is the K2SO4 solid.
Okay. K2 SO4 solid.
And then it's going to yield um, K plus aqueous plus SO4 2 negative.
Okay, SO4 2 negative.
Aqueous, but I think it needs to be balanced.
Okay, so what do I need to do to balance it?
Well, we need to add a 2 coefficient in front of potassium. Wait, is it potassium?
2 coefficient in front of our potassium ion. That is
Correct.
correct. Piece of cake?
Correct.
Simple, right? Not too hard. So you're just breaking it up into its ionic components.
So in this instance, the yield for the products, that yield sign is representing the dissolving aspect within the H2O.
That's right. Or the dissociation. That is correct.
Okay.
Yep. Dissociate means break up. We're breaking up that happy couple. Okay? Water, the homewrecker, is breaking up that happy couple. Okay, so what about the next one? It says write the ions present in the solution for calcium nitrate without writing the dissolving equation. So they just want the ions. What ions are you going to get?
Would you get Ca2 plus?
Ca2 plus. And
NO3 minus?
okay, piece of cake. Yeah, good. So let's make it a little bit harder now that you guys got the fundamentals, right? Yeah, and here you would just write the ions. You wouldn't have to write the, just write them like that. That'll be fine. Okay, so acids. So I've kind of talked to you about acids already, right? So we've been touching on acids a little bit. We're going to talk about it a little bit more today. And thing that we want to know about acids under these circumstances is that acids are just a special case of ion, right? They go through ionization as well too. But here you're using that H. That H is going to be an H plus when it forms that ion. So when we separate it, right? So this is the generic form of an acid, right? These are all examples. So where the H represents that H plus, and then the X represents the negative charge, right? So it's the anion, right? That's going to be associated with the hydrogen. Okay, so if we have an acid, any acid plus water, what we're going to get is the hydronium ion, which is the H3O plus. Now, H is kind of a weird fella, H plus, when it's by itself, it likes to bond to stuff, right? H plus does. And so that's one of the reasons why the acid and it gets together. They're like, oh, you're positive, I'm negative. Oh, I love you so much. Oh, let me grab onto your leg. You're my one, right? And then as soon as it gets in solution, it does exactly the same thing to water. It says, hey, water, oh, you're so hot. Oh, let me grab onto your leg. And then it holds on, right? And so then it makes that water molecule a plus, right? But we have so much water molecule that, it's never gonna collect all of the water molecules. There's only gonna be a fraction of it that's gonna be H3O plus, not the whole thing, okay? So really, we form the hydronium ion, but often to keep it simple for ourselves, we just draw it as, we'll just draw it like this. Let's say HX yields. Yeah. Because it's a lot easier for us to keep track of the H under these circumstances. Do you understand?
Yes.
Are you there? Okay, good. So for simplicity, that's the way we draw it. But you'll see it drawn like this, and you'll see it, here's 2 examples where we're actually doing that, where you can actually see that hydronium ion. But again, for simplicity, it's a lot easier to keep track of how many H's there are if you draw it like this, because otherwise you're trying to balance out the water and stuff like that, and you always end up getting lost in the situation, okay? So you'll see it written both ways. Okay, so a polyprotic acid means that polyprotic means multiple protons, right? So you're losing multiple protons. So this one, sulfuric acid. Sulfuric acid will break up into the hydronium ion and the hydrogen sulfate ion. Then this hydrogen sulfate ion will break up into the hydronium ion and just sulfate. So it's able to get rid of 2 hydrogens, right? Because there's multiple hydrogens that it's able to get rid of, right? So the first one here, this very first reaction, is considered to be a fast reaction. It's going to happen fast. They're going to separate almost as soon as they hit the water, right? So you're going to get rid of that first H. It's going to separate like that. The second reaction is a slower reaction, right? It takes a little bit of time, and they get into equilibrium. So actually what you're going to see is something like this, right? So this guy acts as a weak acid, right? But eventually it's just going to push it over to here, eventually, right? So over time, it's going to separate into its ionic component. Okay, where this one will continuously stay like this until it's a total equilibrium. Okay, questions, concerns, Cash?
Wait, Dr. Henry, can you say that one more time?
So this guy is considered polyprotic, meaning that it separates 2 hydrogens. So say polyprotic acid, meaning, again, separating 2 hydrogens or 2 protons, right? Loses multiple protons. So that means it has more than a single H plus. It has 2 H pluses. So the very first one, this guy's going to happen fast. As soon as it hits solution, this guy's going to be fast. This guy's going to be slower, but it's going to happen slower. And so you're going to get it to a point where you're going to have an equilibrium going on, but eventually it's just going to push over to the total separation. Okay? Where this guy is going to stay in equilibrium. Meaning that you're going to have both of them. Have you heard the term equilibrium?
I've heard
Before?
it before, but never like put it into context.
Yeah. So it's kind of like they get into the point where they're happy with both present. It's kind of like the idea is to get people who are like bipolar or something like that to a point of equilibrium, so that they're not manically happy and they're not manically sad. You want to get them in that middle, right? So they're not having that massive mood swing. So equilibrium is kind of like a stabilizing type of thing. Hey, Jessica, you're doing that again. You're putting your hand on your head. You're looking stressed. Don't worry, it's not that hard. What was that?
I said, I'm just trying to focus.
Okay. Okay, so now we know about the acid. We know that a strong acid is going to separate, it's going to ionize, right? Meaning it's going to favor the ions, okay? So when we talk about that, you're going to have more of the ions present in a strong acid than in a weak acid, okay?
Okay.
So do you think a strong acid is going to be better at conducting electricity than a weak acid, since it totally separates into its ions?
Yes.
Yes.
Okay. And that is true. Okay, so a strong acid basically is going to ionize into the ions, right? So you're going to have that proton, that H plus is going to be free, right? It's going to be humping water's leg, but it's going to be free. It's still going to be that H plus. And then the anion is going to be free to do what it needs to do. So that's going to make it really good at conducting electricity. The major species is going to be the ion. Major species meaning which is the one that you're going to have the most of. Are you going to have most of the ions? Or are you going to have most of the acid that is unionized? Okay. So minor species is the one that you have the least of. So in the case of strong acid, the thing that you're going to have the least of is your unionized acid. So let me give you an example of a strong acid. So strong acid is going to completely dissociate into its ionic species.
Dr. Henry,
Yep.
does dissociate and ionize mean the same thing?
Yes.
Okay.
Yes. Yeah. Ionize is just the fancy way of saying they're going to have their charges, right? And you're going to see their charges. You know, like when they're together, do you see their charges? Do you see charges over here?
Oh, no.
No. So, but I'm just writing all over my board. Okay, over here, do you see charges?
Yeah.
Okay, so they're separating, so those charges are able to be recognized, and you can clearly see that they're charged, right? Because they're separating. Okay, when they're together, they balance each other out, so you never see those charges. They hide those flaws. Okay, you guys get that? So, in the case of a strong acid, you're going to have more of these over here. This is going to be your major species. And so this guy is going to be your minor species. Okay, piece of cake. So what do you think is going to happen in the case of a weak acid?
It wouldn't release protons?
That's right. It's not going to separate, or it's going to separate very little, right?
It would be a
So-
poor conductor?
What was that? It's going to be a poor conductor. That's correct. So weak acids are going to act just the opposite. So hydrogen fluoride, or hydrofluoric acid, sorry. Hydrofluoric acid is a weak acid. Now, the reason why hydrofluoric acid is a weak acid and hydrochloric acid is a strong acid is because fluorine is kind of an abusive partner. It's like, you know, it's telling the hydrogen ion, no, you cannot leave. You stay right here. Know your place. You're right next to me, right? Because it's that bully. Remember we talked about fluorine being a bully?
Yes.
So you're going to have very little separation, right? It's not going to separate from hydrogen unless fluorine wants to separate from hydrogen. The only way that it'll do that is if fluorine finds somebody better than hydrogen. So in that case, which is going to be the minor species? The ions or the ionized molecule?
Would the major
ions?
be the ionized?
Yeah, I know it's right there on the board, right? I was just testing to see if you guys are going to read. So we have, this is going to be your minor species. And again, what does minor species mean?
They're unionized molecules.
Does it mean unionized molecules?
Aren't they lesser of an abundance in the
It means less than, yes, in abundance. And so my major species, it's going to be this guy. Okay, simple. Yay, nay, May, June, July. Okay, so let's talk a little bit about how we know something is a strong acid. So I told you why hydrofluoric acid is a weak acid. Hydrochloric acid is a strong acid because it isn't as strong as fluorine. It's able to sit there and let water loose. Hydrobromic acid is a strong acid. Iodonic acid is a strong acid. If it has ick, typically, this is the only exception. If it has ick at the end, it's a strong acid. Except for like carbon acids, right? So carbon acids are always going to be weak acids. You guys know what I mean by carbon acids? Are you there?
No.
The
Or yes, I'm here, but
so-
I don't know what carbon acid.
What was that?
Yeah, we're here, but I don't know what you mean by carbon acid.
So carbon acids are any acids that have carbon in it, like acetic acid, vinegar. Vinegar is a weak acid, right? So if it has carbon in it, it's a weak acid. Carbonic acid is a weak acid. Citric acid is a weak acid. Proponic acid is a weak acid. Budoic acid is a weak acid, right? So anything that has carbon in terms of being an acid is going to be a weak acid. So all your carboxylic acids are going to be weak acids. Okay. So if it's an OUS ending, it's a weak acid. So sulfurous is a weak acid. Hyposulfurous is a really weak acid. Fluorous is going to be a weak acid. So we'll say weak acids, carbon acids, OUS acids, and we know that this is a special case, hydrofluoric acid. So, who are strong acids? Tell me some acids you guys know. Is hydrochloric acid a strong acid?
Yes.
Is sulfuric acid a strong acid?
Yes.
Is phosphoric acid a strong acid?
Yes.
What about phosphorus acid?
No.
No.
It's a weak.
Okay. Okay, so this is just basically showing you the difference between a strong acid and a weak acid. You see a strong acid makes our light bulb bright, right? Because it's totally separated. You just have your ions in solution, where a weak acid, you have most of your ions are still connected together. So this is most of your acid is still connected. It's not separated. It's not ionized. So this is basically just showing you that. So you guys see, that's acetic acid molecule that's still connected. And then here we only have one set of ions. Okay, so that's going to give you a weak acid, and that's just going to give you a very weak signal, very poor conduction of electricity. So simple. So if you had to do a test to sit there and determine whether something is a strong acid or a weak acid, what are you going to use?
ICNOUS.
No, I said if you had to do a test to determine if something is a strong acid or a weak acid, what are you going to use? So what is a characteristic of a strong acid?
Is it the H3 plus? HO3 or?
Well, isn't that also a characteristic of a weak acid? Doesn't it also form some
A
ions?
bright light?
Bright light. So you could use electricity to determine, right? So if you were in a lab and you were going to test if something was a strong acid or a weak acid and you didn't have a pH meter or anything like that, you could use a little setup like this. If you're at home, you can sit there and take apart your little electricity thing and then stick it in solution and say, okay, does my light work or does it not work, right? Pretty simple.
Yeah.
So light, if it's a strong light, you know it's a strong acid. If it's a weak light, then you know it's a weak acid. Do you guys understand? Because we know strong acids separates into their ions. If they're separated into more ions, then that means that you're going to get flow of electricity much better. So do you understand the thought process? You want to think big picture, right?
Right.
Questions, concerns, Cash? You guys like, you're thinking at the molecular level, you're like, okay. You need to do both, right? Okay, so this is basically telling you everything that I just told you, right? So hydrochloric acid is a strong acid. At 0.1 molar, you have 79% of it ionized, meaning that they're separated into their ions. At 0.01 molar, you have 99% of them separated into ions. So really good ionization going on there. Hydrofluoric is the other way around, right? So at 0.10 molar, it has 9.6% separated into the ions. So that means that it's mostly together. 90% of it is together. At 0.01 molar, 22% of it is separated into its ion. That means that you have what, 78% of it that's still stuck together. They're not separating. So that's a poor. It's going to conduct electricity very poorly. So you can actually you can do calculations to sit there and calculate the intensity of the light and figure out the percentage of ionization that's occurring in that solution. Come on. They don't want you to get past this part. There you go. So the major species for hydrochloric acid is going to be the ions because everything is separated, right? The minor species is going to be the connected hydrochloric acid. The major species of the hydrofluoric acid is going to be hydrofluoric acid, right? The ions are going to be the minor species because you're going to have less of those, okay? You guys see that? You see the difference between major and minor? Good, good, good. Okay. Okay, so these guys, oh, I forgot perchloric. If you have per, it's going to be a strong acid, okay, except if it's a carbon acid. Okay, so when you add an additional oxygen, it makes it a stronger acid. Okay. Okay. So let's see. So ions are going to be the major species in ionic compounds, right? And strong acids. Neutral molecules are going to be the major species, meaning that they're neutrally charged when you have a weak acid, weak base, and water. Okay, so write the chemical formula of the major species write the chemical formulas of the major species in solutions of nitrous acid and chloric acid. So what is going to be the major species in nitrous acid?
HNO2.
AQ?
Correct.
Okay. And what about chloric?
Would be
HCl.
Is it CH?
Or H, would it be HCl?
So is that chloric acid? And would that be the major species?
Oh, no.
I believe the hydrogen's correct.
Okay.
But it
So
needs
you're
to
just saying the hydrogen?
hydrogen is correct, and I think it needs ClO3 negative.
So should H plus, is it what you're saying?
Plus, yes, because
Okay.
they need to balance each other.
And you said ClO?
3 negative.
Okay.
And those are both aqueous.
Okay, that is correct. That's going to be your major species because chloric acid is a strong acid. It's going to separate into chlorate, the chlorate ion, and the hydrogen or the hydronium ion. Okay? Piece of cake?
Yes.
Okay. So what we've done up until this point, we've talked about conventional equations, right? But in reality, what happens when we have stuff in aqueous solutions, they separate into their ions. And that makes them easier for them to interact with each other, Okay, so this is an example of a conventional equation. Right? Now I'm going to show you how to write a dissociation equation or a total ionic equation. Okay, are you guys ready?
Yeah.
Okay, so there are a total of, let's say, 19 people there, and only Matt is the only person that's ready.
I'm ready, Dr. Henry.
I'm ready.
Okay, so we got 4 out of 19. Damn, we're doing good today, aren't we? Woo! That's less than a 5%, you know, that's what? 20%? 20% of the class is ready? That's a problem. Okay, now when y'all get your butt spanks, don't say I didn't try to get you guys included. I want to hear it. Okay, so the way that we would do this, we would separate each one independently as if it's a dissociation reaction. Okay, so this very first one, what is lead nitrate? I'm sorry, lead 2 nitrate going to dissociate to? You there? Lead 2.
Lead 2 plus.
Lead 2 plus. And nitrate?
NO3 negative.
That was really cool. Okay, how many NO3 negatives am I going to have? And I want to put AQ here.
You'll have 2 NO.
Okay. Why am I going to have 2, Ryan?
I believe
Why not 17?
it's because the charge on is it lead is a 2 plus charge.
Okay.
So we're trying to.
So what happens when I dissociate the 2? The lead and the nitrate, what happens?
They neutral out.
Okay. So do the two nitrates separate from each other, or separate because they're only held together because of the lead, or do they combine and I should put a diatomic here?
No.
No. So they separate individually.
Correct.
Okay. Okay, what about sodium chloride? What ions am I going to get when I dissociate sodium chloride?
Two Na plus.
Okay, somebody other than Ryan. I know Ryan is getting this.
Cl negative.
So just 1 Cl?
2
No,
CO.
we would.
Yep, we had to have 2 because that 2 is distributed among both of them. And we want to put AQ. Okay, so anytime that you see a solid, a gas, or a liquid, you do not separate it. It stays together. So all it means it stays together. If it's AQ, it can be dissociated. But if it isn't, that means it precipitated and water doesn't separate it. Water is no longer a factor. So then you would write PB. Cl2. And you put solid. Now, this is going to be really important that you recognize this. It's going to be really important for future things that are going to happen as well, too. Okay? If you guys go beyond Chem 2A. Okay, so what happens here with the sodium nitrate?
Be 2 Na plus.
Okay.
And then 2 NO3.
Negative.
Okay. Okay. So this guy's called your total ionic equation. Okay, so now we're going to talk about spectators. You guys know what a spectator is? So if I come and I just watch, right? And I never participate or anything like that, but I just watch. I never do anything, but I just watch. That's a spectator. So for chemistry, a spectator is the one that you basically have exactly the same ion on both sides. Nothing's changed with it. It doesn't hook up with anybody. It doesn't do anything, right? That's considered a spectator, right? So basically you have it the same form on both sides of the equation. Okay, so can you guys help me find spectators? Who are the watchers?
Two NO3.
Okay, so this guy's a spectator. Anyone else?
Be 2 and A.
Oh, I'm sorry. You said 2 NO3. Sorry, I was ignoring you completely.
Oh,
There you go. So then the 2 Na, since I gave you the answer. Sorry, my brain is it's not snapping right now. So okay, so those are our two sets of spectators, right? We have the nitrate ion and we have the sodium ion. So why isn't the lead and the chlorine ions spectators?
Because they change.
Did you say a physical change?
Well, because it changed, yeah.
Because it changed, right? Or because they hooked up, they came together and they formed a solid,
Yeah.
right? So that makes them different, right? Because they're no longer with who they were with in the beginning, and now they're with someone else. Okay, so we can write what we call the total ionic, or the net ionic equation, sorry. The net ionic equation would be Pb 2 plus 2Cl minus okay, and this guy is called the net ionic. Okay, simple. So the net ionic equation, you just get rid of your spectators. Because really, they just brought the other person to the party so that the other two can hook up together. Okay, simple, good, bad, ugly.
So.
So. Okay,
Yeah.
let's see. You guys ready? Okay. Okay, here we go. Here's our first question. When a strip of magnesium metal is placed in an iron 3 chloride solution, a magnesium chloride solution results and iron solid forms. Develop the net ionic equation for the reaction. So what I'd like you guys to do, first, develop the conventional equation, then develop the total ionic equation, and then take me to the net ionic equation. You guys got it? Okay, I'm gonna give you guys, we'll say 5 minutes, maybe 10 minutes. Hey, we're bargaining here. You guys need 5 minutes or 10 minutes?
10 minutes.
You 10.
You need 10? Okay, take a picture of the question. Okay, so then I'm gonna put you in your groups.
Okay, so we would have to start out, well, we would have to name.
So the first thing we need to say is magnesium,
Right.
Mg.
And that's a solid.
Right.
Let me draw. Okay.
Plus iron chloride, which is going to be AQ in parentheses.
So it'd be FeCl. Three. And then in parentheses, AQ. And then you would
And then your yield arrow.
A.
And then you would do MgCl2. And then that one would be aqueous. And then plus Fe. And that's a solid. Okay, and then you have to,
Is it balanced?
well, we would have to include the numbers in front of the elements that were given. So for the first Mg, that one would have 3. So it'd be 3 Mg. Yes. And then for FeCl3, that one would be, I got 2. And then for in front of the MgCl2, I got 3. And then in front of the Fe, I got 2. And that is what I got for the balanced equation. And then for to develop the net ionic equation.
Wait. Hold on. We'll let somebody else do it. Good job. You guys did a good job. Good job. Group number 3. Okay, you guys do the total ionic equation? That's, I'm sorry, Andy's group, Guadalupe's group, Jocelyn, and Juan.
Got.
Yeah, you guys.
All right. You're gonna have 3 magnesiums.
Magnesium. 3 magnesium. S.
Is there going to be a charge on it?
Uh,
No charge. So magnesium.
No.
2, no charge. So,
this one's 3 plus.
That one is a 3+ charge, yes. Six chloride. And then 3 magnesium. Then that one will have the charge. Plus the 6 chlorine. Negative. Aqueous. Plus the 2 iron, and that will become a solid.
2. Yes.
Don't forget your E in iron.
Oh yeah.
There's 8 on. No, you don't put 8.
There you go. Okay, good job, good job. Okay, group number 4.
Total.
Group number 4. Give me the net ionic equation. Or no, first identify the spectators. Group number 4.
So would the spectators be
1.
3 mg?
Nah,
That'd be the chlorine, no?
The
yes,
chlorine.
it would be the chlorine. Is that the only one?
Let's see.
Yeah, I think so.
Yep,
1.
it would be the chlorine only. So why wouldn't it be the Mg? Why is the Mg an incorrect answer?
Solid and aqueous.
Yeah, because it's
I'd
going
change
from a
it.
solid to aqueous, and also the charge, right? It's going from neutral to an ionic charge. So that's the reason why it wouldn't be. Okay, so group number 1, that would be Judy's group. Judy, Anna, David, and Aaron. Can you guys give me the net ionic equation?
Um, 3 mg.
Well, you write it down there.
Oh, okay. I'm sorry.
Come on, I'm taking my break. This is my coffee break.
Okay. Let me perform.
Oh, I need coffee too. Oh my gosh. Ah. Ow. Damn it.
Nathan's rock.
Oh.
Sorry. I thought I was on mute. Oh. Oh, that looks like a sad too. Hold on.
Okay, while he's writing it, one of your group members need to explain it. Come on, Aaron, or Anna, or Judy.
So for the net ionic equation, I've written down this because for the net ionic, we are going to take out the spectators, which is 6 Cl minus AQ, and it was the most abundant.
Is that the reason why we take it out?
Yes, but I can't remember the explanation for it, but that is what you're supposed to do.
Okay. So why are we taking out 6 chlorine? Anna or Aaron?
I think because they appear on both sides of the equation
That's right, because it appears on both sides of the equation in the
as
exact same form.
yeah.
Yep.
Yeah.
Yeah. And they're the exact same form. So that's the reason why we take it out. Not because of the abundance, it's only because your Cl, you have 6Cl minus here AQ, you have 6Cl minus Cl AQ over here. So you take it out of the equation since it's on both sides. Exactly the same form. Where the magnesium is going from magnesium solid to magnesium 2 plus aqueous. So it's going from a metal to an ion, and then that's the same thing with the iron. The iron is going from an ion to just the metal itself, a neutral metal. Okay? Okay.
Dr. Henry,
Yeah.
will you just say that one more time? You said the spectator is Cl because it's on both sides, and what was the other reason?
And also that it doesn't have a changed form. It's exactly the same form, right? So we have 6Cl minus over here, AQ, and you have 6Cl minus over here, AQ, right? If you look at the magnesium, right, it goes from, you have 3 magnesium solid to 3 magnesium 2 plus ion, right? So that's changed.
Okay.
Okay, so it has to be exactly the same for it to be spectator on both sides. Questions, concerns, cash, credit. Okay, can I erase and move forward?
Yes.
Excellent. Good job, guys, good job. So let's move on. Okay, so now, let's go back. Okay, if you look at this one, I want you, so what is the total net charge of the magnesium here on the reactant side of the equation?
Neutral?
It's neutral. So I'm going to put a 0 for neutral. What is the total net charge over here for the magnesium ion, the 2 plus ion?
2.
Okay, so it's going to be a +2. Okay, what about the iron over here?
3.
So it's going to be +3. And then what about the iron over here?
0.
0.
Who's zero?
0. Yep, because it's no charge. Okay, so this is going to be kind of important. So if we lose electrons, and I like saying Leo, so loss of electrons. So loss of electron is going to be oxidation. And then gain of electrons. That's going to be reduction.
Reduction.
And I say GER. Okay, so if I'm going from 0 to +2, is that going to be oxidized or is that going to be reduced? Are we gaining electrons or are we losing electrons?
Reduction.
If I'm going from 0 to +2, am I gaining electrons or am I losing electrons?
Gain.
Oh, reduction.
Are you sure?
Losing.
So if I'm adding, because what is the charge on electrons again?
Minus charge.
It's a minus charge. So I'm going 0 to +2. Is that gaining electrons?
Losing.
Not losing
It's
electrons.
losing electrons. So this is a Leo, right?
Oh,
So we're losing electrons, right? If I'm going from +3 to 0, what am I doing?
gain.
I'm gaining electrons, right? Because that is a positive charge. The only way that it's going to become a 0 charge is if we add electrons to it, right? So our magnesium is being oxidized and our iron is being reduced, okay? The iron ion is being reduced because, okay? So oxidized and reduced. So this is called a redox reaction, oxidation reduction reaction. And this is when electrons are being transferred from one species to the other species, right? So in this case, we're losing electrons, so we're taking the electrons from the magnesium and we're giving them to the iron. You guys see that?
Yeah.
Okay, good.
What kind of equation did you call that?
Redox. Stands for reduction or oxidation reduction reaction. Redox. Okay, so let me give you an example, another example of a redox reaction. Okay, it says an iron nail is dropped into a solution of hydrochloric acid. So let's write the conventional equation. Okay, what does an iron nail look like? What is the chemical formula for iron nail?
Would it just be Fe and then in parentheses in S?
Okay. And hydrochloric acid?
HCl, and then in parentheses, aqueous.
Okay. And what are we going to make?
So you would yield that. Mm.
What type of reaction is this?
Is it single displacement or replacement?
Single displacement or single replacement? Yes. So who's going to replace who?
Does it matter which
Iron.
one you start with?
It doesn't matter who you start with.
Okay, so for iron, would it be, if you were to change iron, would it be FeCl? Because you'd be replacing the H.
Uh-huh. And when you, based upon everything that you've seen so far, it will be Fe 1, 2, or 3.
Fe. Would
Since
it
we
be
talked
2?
about, try one more, higher.
3?
Yes.
Wait, why would it be 3?
That's the one that's more commonly stable. And you can kind of base it on all of the questions that we've answered so far. We've had Fe3.
Oh, yes, you're right.
Although Fe2 will exist, but it's usually hydrated, so. Okay, so Fe, is it?
That one, would it say aqueous?
That's right. And what else are we gonna get?
And so we're left with hydrogen, so that's just H.
Okay, so tell me about hydrogen, since it's just H. What is it gonna do?
It'll have to be H2, wouldn't it?
That's right. And we know H2 is a solid,
Gas.
liquid, or gas.
Gas.
There we go. Good job. But it's my turn though. Okay, is it balanced?
No.
No.
Okay, so what do I need to do to balance it?
So that has H2. So would you add a 2 in front of HCl?
Okay. Was that balanced?
No. You need. Oh, and
So like right now we have what? 1 hydrogen.
and
How many? We have 2 over here.
yes.
Chlorines we have on our reactant side, we have how many?
1.
And then over here,
3,
and then iron
1
1,
and 1.
Okay. So what do I need to do to balance it?
Would you add a 6 next to HCl?
Okay, sounds good. Make my 6 a little bit better. Okay, got a 6 in front of HCl. Is it balanced now?
No.
No. Yeah.
Okay, so what do I need to do to balance it?
So
Put
you,
a 2
To
Next-
where?
In front
in
of.
front of F3.
Okay, so then that gives me 2 here, 6 here. Is it balanced now?
No.
would
Put
you
a
add
2
it?
in front of iron and a 2 in front of H2.
And you said 3 in front of H2?
2.
Yeah.
4.
3.
3, yeah, 3.
Yeah, 3.
Okay.
Okay, it's balanced, right?
Yes.
Okay, so let's do the total ionic equation.
Okay, so you would have so would you just start off with Fe?
How many?
2.
2.
Okay, yep, we leave it exactly the same, and since it's a solid, there's nothing to break it down to, so
Oh, okay.
2s, okay.
And then plus
H plus aqueous.
You said 6, and you said each,
Yeah.
so you're saying each ion? Is this what you're saying?
Mm. Yeah. And
Okay,
for H, you would have the plus charge, and for Cl, the minus charge.
okay. And that's going to yield?
Um,
would it be Fe 2
Like that?
no.
No? Okay.
No.
Two Fe? 2 in front?
Yes.
Okay. And since this is aqueous, it's going to make what? Fe what? What is going to be the charge on it?
Would it be plus?
Just 1 plus?
2 plus.
2 plus? Are you sure?
No.
3.
I heard somebody say 3. Should be 3 plus, right? Because it takes 3 of the chlorine to balance it out, right? So then, how many chlorines do I have?
6.
I'm pretty sure that was 6. Because I heard X. And that's AQ. And then what do I do with the hydrogen gas?
Does it
Leave it.
We
You're just
leave it. That's right. We leave it alone. You make me so proud. You guys actually listen to me sometimes. Okay, so this will be our total ionic equation. Who are our spectators?
so your spectators are the ones that stay the same, right?
Exactly the same.
That
Yes.
would be your 3H2. Wait,
would it be your 6Cl minus?
Okay,
Oh,
so,
yeah.
yeah. It's on both sides, right?
yes.
3H2 isn't the same on both sides because here it's 6H plus,
no.
right?
Yeah, you're right.
Okay, so then our net ionic equation is just going to be the ones without the spectators. So it'll be
FeS plus 6H. Aqueous
3 plus.
Plus 3H2.
Okay, now here's the hard question. Who's being oxidized? Who's being reduced?
Would it be?
So this guy would be a 0, right? Since it's has no charge associated with it, so overall it's going to be a 0. So you're going from plus to a 0. That oxidized or reduced?
Oxidized.
Okay, what does oxidized stand for? What happens in the case of oxidation?
You lose electrons.
Reduces.
I'm losing an electron. So if I go from a plus to 0, so plus 1 to 0, am I losing an electron?
No, you're
No.
gaining.
I'm gaining an electron. So this is GR, right? Which means reduced. Okay, so then by default, if I go from 0, this guy is 0, to 3, plus 3, is that oxidizing or reducing?
Reducing.
0 to plus 3.
Oh.
Losing 3.
Okay. So
Yeah.
it's losing, right? And so that's Leo. Okay,
Oh,
you get it?
Right, down this.
Okay, so the answer, this is the final answer for the total ionic equation, but we know that iron is being oxidized and hydrogen is being reduced. Okay? Questions, concerns, Cash? You want to try one more?
Yeah.
Yeah.
Yes.
Okay. Next. Okay. So we have this reaction, the reaction between zinc and the solution of copper 2 nitrate. Okay, so write the total equation and then tell me what is being oxidized and reduced. Are you there?
Yes.
Okay,
Yeah.
so I'm gonna put you guys in groups and you guys can argue it out. How long do you need?
There we go.
10 minutes? 5 minutes? 20 minutes? Actually, we'll give you a couple of them. You said 20 minutes?
20 minutes.
Yes.
20 minutes. I'm going to give you one more problem too, so then we'll make it worthwhile. So let's say, Give me 1 second. Okay, my lab kit just came, and it is so tiny. Makes me wonder.
Mine's still outside. I haven't gone to get it yet.
What was that? Spray the box.
As it,
Because if
Oh,
it's
yeah.
coming from, yeah,
mine's sitting outside. I'll go get it in a second.
yeah. Okay. You guys got it? Are you ready? Okay. Go for it. Got my board. We'll do it like this. We'll cut it in half. And then on the other side, okay, so group one and two over here, group 3 and 4. So group 3, you guys are going to be responsible, and that's Deandra's group. You guys are going to be responsible for the conventional equation, the total ionic equation, and the the conventional equation and the total ionic equation. Group 4, you guys are going to be responsible for the net ionic equation, and you guys are going to tell me what is being oxidized and what is being reduced. Okay? Go team, go.
Who's in group 4?
Group 4 is Jessica's group. Jessica B.
Okay.
Oh, Jamie can't hear anything.
What was that?
Maybe, I was saying Jamie can't hear anything. Maybe she can restart her computer. I don't know. She wrote in the chat.
Why am I not seeing?
Okay.
Okay. Go teams, go. Hold on.
Okay, maybe I'm confused. Somebody else is doing the net. Who's doing the net ionic?
I'm doing the. The one in blue.
Yeah, the best sister. She got me Starbucks and egg bites.
Who did?
My sister.
Oh, that's so
Oh,
nice.
sweet.
Yes. She told me to tell you guys hi.
Oh,
tell her
hi.
good morning. She's starting the day right.
That's right.
I know. Gotta love
It's
siblings.
sharing it with you.
Yep.
Okay. I'm doing the same thing as somebody else, and I don't know who it is, so I think I might be confused.
Are you guys
On which one is
communicating with
what?
each other?
I'm
Which one
trying
are you
to. I
trying-
don't know who's writing it.
Oh, I wrote
The one on the bottom.
I'm doing the iron. Is that the one you're trying to do, Jessica?
Yeah, but I don't know. Okay, maybe I'm confused on which part I need to be doing.
Because group three was supposed to write the conventional and the total ionic. And I think I was in group 3. Dr. Henry said group 3 was Deandra's group.
Okay, so what, Dr. Henry, can you tell me what group 4 is supposed to do again?
You guys are going to do the net ionic, and then you're doing the, tell me which one is being oxidized and reduced.
Okay, so I am doing the net ionic.
Yes, net ionic. Yep.
Oh, shoot. Who did I was writing the conventional. Oh my goodness.
You
Okay,
do
let
not
me erase.
communicate well with each other.
I know.
Communication is an essential part of things.
Okay, so I'll just, that's probably a lot neater than my mess, so.
You guys agree? Everybody agree with the conventional? What do you guys know about iron so far? It's been very consistent about iron.
It's a solid.
Well, here it's a solid, but when it forms an ion, what ion has it formed so far?
3.
Okay. So I may want to keep that in mind. Okay, let's see. Okay, that is correct. Down here for your net ionic charge. Loss of electron, gain of electron. Good job, good job. Okay, so who wrote the total ionic equation for the iron and the silver?
I did.
So you may want to take a look at that. But are you forgetting anything? You may want to take a look at that. Again.
Was my 3NO3 wrong?
No. Well, yeah, if it's the net ionic equation, it is. Wait, you're the green?
Yeah.
You're the green. So yes, it's wrong if it's the net ionic equation. So let's talk about this guy right here. Let's see. I know you guys aren't finished. You're in the process, but I'm gonna. Okay, this right here is wrong. This whole side is like a hot mess. You're forgetting a lot of things here. And then, is this balanced up here? Let's see. Okay. All right, Zinc guys are did a good job. Good job. Good job, Zinc. Okay, now I want you to go ahead and do the breakdown of what we do, our skills of breaking each component down, and you're going to tell me that it's balanced for the iron guys. Break it all the way down. You can do it on top where I have the question marks. And then this part here, Let's see. Are you finished, Juan?
No.
Okay.
Want me to finish it?
Yeah, go ahead, finish it. Yeah, you want to make sure you're using a capital N too for that Juan, right? Instead of a lowercase n. So would that be the net ionic reaction, or would that be the total ionic reaction, Juan?
It would be the net.
Okay. So we're going to fix the first one. Do you guys see what's wrong with it?
Yes.
Okay.
One second. So by breaking it down, do you want me to put like how many of each, the way we usually write the elements?
Yes.
Okay.
Yeah. Or you could even do it in terms of the ionic polyatomic ions as well too. You could do it that way as well too.
Just had to redo it because I had it wrong.
Oh my God.
This side. And then AG has 1. And then that NO3, that 3 on the outside of the parentheses should be a 2.
Okay. You're saying here?
Yes.
But is it, most times iron is going to interact, it's going to form a 3. It will form 2 sometimes, but so far we've only seen 3.
Okay, so will that make a difference?
Yeah, it's going to
Oh,
make a
wait,
difference.
yeah, you're right. You're right. Okay, so then NO3, this one would have 2. So that's, so if you were to add, so would you add a 2 in front of AgNO3?
Okay. Would I add a 2 or would I add a 3?
Or 3?
Okay.
Yeah, because what? Yeah. So that would be 3AgNO3.
Okay. And then,
Yeah.
so then how many AGs will I have over here then?
3.
3.
Okay. So that's it. It's balanced now. Okay, so now how do we fix our total ionic equation? I always like doing it. I'll draw my line. Okay, I got that guy. And then I know these guys are splitting up, right?
Yes.
So what should be this guy? Is this a solid?
An aqueous.
No.
Aqueous.
Be aqueous. And then that also means that it should probably be a, what charge?
Positive.
Okay, so that takes care of that. What about this guy? What happens here? Oh, can you just throw iron out the window completely?
No.
And then if iron is what's keeping these guys all together, so then these guys are going to be separate. Let's see if I can make some adjustments to give us a little room to work. So what did we forget for this guy on the other side of the equation?
Iron.
Iron. And is it going to have a charge?
Plus.
Plus what?
Would it be a
3, 2.
Plus 3. That's right. That is correct. Oops. Just going to erase it all. Okay, so iron 3 plus. AQ. And how many of these guys am I going to have?
3.
Yes. So we're going to put the 3 in front because here it's only like this because the iron holds it together. Remember, the ionic reaction is what's holding that together. As soon as you disrupt that iron reaction, they're free to go and they're going to act as individuals. You're going to have 3 of those. Okay. So then our net ionic equation. Oops. So how many of these guys do we have? We have 3. Right. And 3 of these guys. Yeah. Okay, so we have 3 and then 3 of these guys over here, right? So this guy and this guy are exactly the same. They're spectators. So So then our net ionic equation is going to be
Solid.
that's a solid. That looks like fecal. Never mind. Let me fix that because that looks really bad.
It's too small. I can watch out.
Plus 3 Ag plus AQ.
L6. And then
Okay, so who's being oxidized and who's being reduced?
Iron is oxidized.
H.
That's right.
Iron.
Iron is oxidized.
Silver is a reduction.
Silver.
Silver is reduced.
Reduction.
Okay, piece of cake.
No.
Why not?